Hello, everybody. Thank you so much for coming today. My name is Sarah Lynch. I'm the marketing manager at PSIM. And yeah, I'm glad that you all found your way to us today. We have a great webinar prepared for you where Albert will show you a little bit of an intro on how to use PSIM to simulate power electronics and yeah, a little bit of tricks on how to get started, everything like that. And of course, which is also interesting for everyone who is maybe already familiar with PSIM, is that he will look into some of the common mistakes that people make with PSIM, and then maybe they blame the software even though they just did something wrong. So we want to make sure everyone knows how to do everything. What are the common mistakes? The webinar will hopefully get you some good insight for that. So I think that's basically all you need to know. Now I will give the microphone to Albert, and yeah, have fun.
Oh, okay. Thank you, Sarah. Yes. Okay, so let's get cracking here. We are going to look at how to simulate power electronics with PSIM. I don't really know if there's any more way that I can sort of fill in on that anymore, but yeah, so let's try to kind of talk about simulation for a moment here. Like what is the point of simulation? Simulation allows topologies and control strategies to be investigated without risking life, limb, or hardware. Okay, so if you're trying to simulate a 10,000 volt power converter, or trying to build a 10,000 volt power converter, I probably want to simulate that first, because power devices exposed to that level of voltage, if they blow up, will vaporize things. So definitely don't want molten copper spraying on me. Also, those things, when they blow up, sound like a gunshot. So I mean, it could be pretty scary simulating, designing some of these things. So simulating it first, making sure that everything's going to be happy and not break is an important thing. So when it comes to simulation, we always kind of need to ask ourselves, what am I simulating and why, and what am I hoping to learn from the simulation? So some tools abstract implementation details away. So make it easier for you to actually test a concept. So that's things like gate drive or parasitics, reality. Abstracting that information away allows your simulation to be easier and your initial design process to be easier, because you're not trying to deal with these interactions that potentially will break things or stop things from working in real life. I mean, you need to get to those things, but if you're just trying to see if the topology works, there's no point dealing with inductor saturation or something, or gate drive noise ringing when you're just trying to see if something works. Like you need to separate, divide, and conquer. So and so some tools also allow you to include that kind of reality into your simulation. So PSIM is now in its unique form is allowing you to work with ideal models and simplifications, and it also allows you to introduce non-ideal models and some of those parasitic impacts. So definitely, PSIM allows you to introduce non-ideal things and high-frequency interactions and all that kind of stuff when you're ready for them. It doesn't force you to deal with those things in your first design process. Okay, so simulation disadvantages. Junk in equals junk out. If your simulation premise is flawed to begin with, then your simulation output is going to be flawed. So if you do a poor job of setting up a simulation, then you're going to get bad results. In my opinion, there are three things. I'll get to those in a second, but so I've got some three highlight things here that I'm talking about here. Let me pull up my laser pointer. So we've got digital control versus analog control, impact or delay. These are some typical things I see that people don't respect. That's digital control versus analog control. That's ideal DC sources versus a real DC source, in this case like a PV panel. Controller bandwidth. So people designing controllers and not really kind of getting what's happening. So having a controller bandwidth, which is incredibly fast, you'll end up with a stable system, quote unquote. And we'll look at that in a second here. And then another thing is that people just dump in so much reality to begin with that it prevents them from actually achieving their first order design goals. Next up here. So these are the three things that happen, that is the root cause of simulation that doesn't work properly. User error. So the user has done something and they can identify it, or they can identify it. So that's bad settings. So the simulation length is too short, or the time step selection isn't very good, or their switching speed. They meant to switch at 10 or 100 kilohertz, and they're switching at 10 kilohertz. You know, their topology isn't wired connected properly. You know, these are all kind of identifiable bugs. Some of them are easier to find than others, but basically the user has done something wrong in the simulation. And the second reason, and this one, people like to blame the simulation engine quite a bit. Typically, most simulation engines are pretty good and don't have very many bugs. PSIM has been around for 25 years. LT-SPICE has been around for a long time. So, you know, SPICE in all its iterations. Simulant's been around for a long time. Plex has been around for a long time. I'm going to let all of these simulation tools have been around for quite a long time. So yes, bugs do show up, and there are limitations in models, and there are convergence and other numerical issues, but in general, most simulation tools work quite well. But, you know, occasionally there are bugs in the program. Occasionally there are limitations to the model that you're using and what it can perform. And there are, in some cases, convergence or other numerical issues. So PSIM lacks, because of the way PSIM works. PSIM was specifically designed to simulate power electronics, where it's not devolving the simulation into state-space matrices that get solved independently. When you do an independent solve of state-space matrices, there's an interface. That interface delays information from one matrix to the other, and that can have issues when there's big derivatives in systems. So whenever you turn a switch on or off, you introduce a derivative in the voltage and current. That derivative, with state-space matrices, you can have issues where those matrices won't converge anymore. They won't solve. So you need to take a really small time step in between, and that can lead to issues in the state-space matrix approach when there's lots of switches going on and all that kind of stuff. PSIM does a simultaneous solve of the power stage. So those sorts of convergence problems related to those sorts of things don't exist with PSIM. And so then this one here, point number 3, simulation exposes a fundamental design flaw or lack of understanding that the user thinks is a simulation engine problem. This is all too common, that people come to us with issues in their simulations and they are blaming the engine when really it's them who don't understand. I'm not going to name names, but I've been here for 7 years doing this kind of stuff, and this is quite common. So clipping along here. So digital control. So my next point here. So if we come back on my slides here to some of my favorite issues that people come up with. So digital control versus analog control. This one here. So digital control system based on microprocessors update the duty cycle at the beginning of the next period. So as opposed to an analog processor, which is kind of an instantaneous, you've calculated your new duty cycle and it's used right away. With digital control, it's that register needs to update at the beginning of the next period. So that concept is sometimes lost on a few people because this is adding an extra delay into the system. So simulation allows this to be seen. So you can simulate that kind of thing with PSIM. You can simulate the digital control and the delay and see what impact that's going to happen. And another quick look here at a PV panel. So a PV panel, we can see the relationship here between the voltage and current. So it can supply, very happily supply 4 amps, and there's a maximum power point here. But we can happily supply 4 amps until about 11 or 12 volts, but then it falls off a cliff. So trying to use an ideal DC source to model this is not really going to work. You can use an ideal DC source to kind of get a feel for things, but treating a PV panel like an ideal DC source is going to lead to failures. And a PV panel is just one thing. I've seen issues where people are going to series stack power supplies. So they'll have, say for example, a PFC front end, and then they've got another conversion stage, and they design the PFC. That works fine, and then they go ahead and they are designing their second stage with an ideal source, and then they neglect the interaction between the two. I've also seen instances where someone is designing, where someone's doing a microgrid, and they design their three-phase PFC, for example, off of an ideal or infinite DC three-phase source, and then they go ahead and they put their PFC now connecting to a microgrid developed one, so something that's a three-phase source that's developed off of switching inverters or off of active rectified PMSMs or something like that. And all of a sudden there's an interaction between those two, between those things that wasn't considered before. So if your system is going to be connecting to another converter, you can do some design work with that ideal source, but moving to the next stage is going to be having multiple converters working with each other. So this is a common issue. The next one is my favorite. This is the controller bandwidth problem. So PSIM is pretty robust when it comes to simulating these things. So we allow, the engine can really handle a lot of junk in the simulation that other tools may throw garbage out or not work on. So if we look at this, if we look at the left-hand figure, we see, say we're controlling, this is being controlled to 1 amp. This is an inductor current being controlled at 1 amp here, and it looks okay. But if we look and dive down into what the actual converter is doing, we see that there's bad business here. We see, so the red line here is the modulation waveform. The red line here is the modulation waveform, and the blue line is the carrier waveform. And we can see that the modulation waveform is bumping along here on the carrier, and we can see that that's being reflected in the gating waveform. So the gating waveform, we can see is actually switching 5 to 10 extra points per cycle here. You see every single time it goes across the blue line, it's going to trigger a switching event. So instead of controlling the inductor current with the proper duty cycle, it's being controlled by basically doing some sort of pulse modulation. So this won't work, because I mean, if this was supposed to be 250 kilohertz switching, now we're switching in the megahertz all of a sudden, and that's just going to drive switching losses through the roof. So how much detail is required? So again, this kind of cycles back to our initial reason for running a simulation. What are we trying to do? Are you trying to verify the topology? Are you trying to verify how much energy storage you need, like inductor and capacitor sizing? Are you trying to design control loops, or are you looking at device losses and thermal steady state? And then you ask yourself, do I need an ideal switch transition, or do I need a realistic switch transition? Do I need to model lead package inductance or those sorts of things? Sometimes no, sometimes yes. So for these simulations, we don't need a realistic switch transition. Device losses is the gray zone there. So device losses, thermal steady state typically happens after a few hundred or thousand switch cycles to get to everything after everything hits steady state. So you have your electrical transients resolved, and then your thermal transient is longer time periods than that. So PSIM has thermal models that idealize the switch transition, but still calculate those losses and push out to a thermal equivalent circuit so that you can get to thermal steady state without sitting there for minutes or tens of minutes while waiting for a simulation to finish. Okay, so now we're going to kind of get into some time step questions, and we're going to start looking at a few simulations here. So all of the simulations that I'm going to be working with here are going to be available afterwards. So when this webinar is finished, you'll get a link to a page that hosts the recording, and on that page will be further like download button where you can download my sims. A bunch of my sims are not really like real sims; they're just kind of demonstrations. But so let's kind of talk a little bit more about time step. So PSIM has two options for the time step. We can run a fixed time step, or we can run the dual time step. When we run fixed time step, this is a common question. It's so the coarseness of the time step, does that impact my resolution or my results? And the answer is sort of not really. It all kind of depends. So let's look at a simulation that deals with that. So coming out over here, let me find my sim. Okay, we've got a converter here. This is just a simple buck converter. We've got a fixed duty cycle here, and we've got a frequency source, 250 kilohertz. Okay, the time step in this simulation is 200 nanoseconds. So we do some math here. Let me pull up my calculator. Slide this over. Okay, 1 over 250K is 4 microseconds. We're running with 200 nanosecond time step. So divided by 0.2 micro, that is 20 points per cycle. Okay? So this simulation has a fairly coarse time step, 200 points, so 20 points per cycle. And there's a fly. But so, are we going to be able to only resolve 20 different duty cycles? Or what actually is going to happen is that PSIM is going to interpolate. So we will have a coarse time step, but PSIM is going to interpolate to find the exact moment of transition so that the average values on in this inductor, so the average current and voltages are going to be correct. So even though we have a coarse time step, and if we look at the simulation results, we're going to see like a gating wave, like it's going to be displayed in discrete chunks, we'll be able to still resolve very subtle changes in duty cycles. So let's have a quick look at that. So I'm running this in free run mode. So when it comes to the simulation settings here, I'm using, let me find my little drawing tool, pen. So I've got this checkbox on here, and this is, so there's no end time, okay? So what's happening is I'm running this simulation without an end time, and it's basically like running a power converter on my bench, on my test bench. Let me just delete these little drawings, erase drawings. I've got my tool back. Okay, so, and what that means is I can load up this oscilloscope and we can see this waveform. Actually, let me change this so we can see the actual, how it kind of does this. So we'll turn that on, we'll stop it, and I'll restart it so you can kind of get an appreciation for what's going to happen here. So I'll start this simulation, and we can see that we saw that transient there. We could have triggered on that if we wanted to, but now we're in steady state, and I'll zoom back in here. And while we're running, I can change the runtime variable. So we're at 50 microhenries right now. If I were to go up to 100 micro, we would see that ripple change. And if I go down to, say, 10 micro, we can see that bump up again. Okay, so let's go back to 50 micro where we were. And I'm going to set the offset here so that we can kind of zoom in a little bit and really see these differences here. Okay, so that was playing around with the inductor value. Now I'm going to change the duty cycle. So so we're down to, so this is per unit. So my modulation carrier waveform is 0 to 1. So right now we're running with a modulation waveform of Right now I'm running with a duty cycle of 0.26, so 26.5%. Okay, so we could drive that even a little bit lower. So what I'm going to do is I'm going to subtly change the duty cycle. So I can change this runtime and then look over here as we go, and you're going to see as I increase the duty cycle that the average current is going to slowly creep up. So again, we're running with the course time step, so 20 points per cycle. So the interpolation is happening and we're finding the exact moments there, and we're able to accurately provide you with what that average current in this inductor is going to be. So definitely if we look at the sim results, we're going to see, so let's go back and look at just at a transient simulation. So stop. And if I run this and we just look at the transient simulation, we'll see IL is there. Maybe we'll run a little bit longer. Come back out over here. So, and if I pull up the data points, we're seeing, 20 points per cycle. So maybe we're not quite grabbing the peak or what it might be. But then we can come down here, and if we're looking at the gating, do I have the gating? No, I don't. Sorry. Let's pull up this. Pull up the gating Q. There we go. So we can see the waveform is a little bit deformed, but if we're just looking to see, it all kind of cycles back to what the purpose of the simulation was. If it was just to kind of verify how things work, if we're just trying to, there's a couple questions coming in. I see questions. I'll get to your questions. I've got other things coming up here that addresses those questions. So let's pull up a marker here. So we're looking here at, so we've got this coarse resolution of the duty cycle, and we've got this somewhat deformed current waveform, but the average value is, everything is working and making sense. If we care about more resolution, if we care about things beyond just if this thing works, then we can start adding in more time points, maybe getting into 100 points per cycle or 200 points per cycle. Or if we switch to a level 2 switch model, maybe we need to drive down. We're no longer looking at these large-scale simulations, and maybe we need to drive to, if we're looking at a GaN device or a silicon carbide device, turn on and off, maybe we care at a nanosecond time level, okay? Now, the other thing we can do is we can switch to a variable time step or the dual step. So if we copy this over, we can have a fairly coarse time step. So let's put that at say, that's 10 microseconds. That might be too big. So we can go to 2 microseconds. So if you remember, our period was 4 microseconds on 250, and we can dive down to say 20 nanoseconds at the switch ratio. So what the dual step engine does is, what PSIM knows is it knows when the devices are turning on and off, because these are ideal switches. We're sending an on-off signal. So we know that exact moment, and the engine will switch to a smaller time step at that point. So here we are running again with a very small time step now at those transitions. Oh, and this doesn't look very good. I just was doing this blind. I should have set this up. So we have far too coarse a time step in between here before we switch to the smaller time step. So this was a poor, I hadn't run the simulation beforehand, but we can see the detail on here. And again, these are the sorts of things that one needs to understand when you're using a tool, is what the impact will be if you go with really bizarre settings. So I was trying to, I hadn't done that beforehand. I was just trying to really show a difference there, but yeah, too much. So we need to have a smaller ratio between the coarse step and the fine step to get that kind of resolution. I'm not going to fool around with that too much because I've got a whole set of other simulations to look at. So the next thing to consider, so there's some questions coming in Did you add a new probe without rerunning the simulation? No. So if you're going to run a probe, you have to add, if you're adding elements, you need to add that in and resimulate. There is an option if you want to save all waveforms, you can save all voltages and current waveforms. So there's an option right here in the menu. So that was in settings. So if you go up to options, you have this option right here to save all voltages and currents in the simulation. I don't recommend doing that when your simulations get large because you'll start to run out of points, or it'll start driving a very large results file and the simulation will start to slow down. So minimum time step requirements. So that's this note right here. So minimum time step is driven by the fastest known analog frequency, so that's going to be 10 points per period, the fastest known digital frequency, 1 point per period, or any short pulse duration. So the fastest of all of these. So in this example, I'm running with, so I've got my 20 points per cycle again. So if I run this simulation, we're all happy. So we've got our output voltage. Okay. If I switch this off, if I switch this element away, so that was our carrier waveform, and I grab this one. So this one now has a 0.99% duty cycle on that ramp. So that 0.1% is going to drive a small time step. So this is going to drive a 40 nanosecond time step because we need to get a point inside of that. So if we run this now, it's actually gone for 2 points inside of that. So our new time step is now 20 nanoseconds. So we've actually, it's driven a smaller time. So we've driven, I should rewrite that. We've had to put 2 points inside of that very small pulse. Okay, so that's one thing to consider. If we come back up to my simulation control here, and let's change this back to 0.2 micro, and if we swap this back in. So one of the things I'm doing here is I'm enabling and disabling these elements. So you can see they're grayed out. That's if you click on one, there's this green and red X up here. And I'm also using hotkeys Control D and Control E. So now with a digital source in here, so 10 megahertz, the period of that. So this is going to drive our time step now. We're at 0.2, so 200 nanoseconds. This is going to drive our time step because we need 1 point there down to 100 nanoseconds. So these little warning messages will pop up and say you need to change these things. So we'll come back over here. And then other things that this will impact is if you start using square wave sources, if you put little tiny duty cycles in here, that's going to drive minimum time step. If you start using dead time, this is going to drive small time steps. Monostable flip-flops, if you start putting small pulse widths in here or small little delays, you kind of need to be cognizant that putting in small little pulses is going to create small time steps. And so the typical issue is when people start playing around with dead time. So you don't need to simulate with dead time if you're simulating with ideal switches. It doesn't help anything. Again, you need to cycle back to what the point of your simulation is. If you're just looking to see if your control loops are stable, if you're just looking to see that things work, you don't need dead time. Getting into dead time is you don't even need dead time if you're looking at zero voltage switching or resonance switching. Obviously you would need to put it in eventually, but you don't need it if you're just looking at kind of the larger system level. So definitely one thing that I see people doing quite a bit is they start adding in dead time way too early. So you don't need to do a control loop simulation. Again, it's about divide and conquer. What's the point of the simulation? And do I need to have a really small time step for it, or do I need to have a really big time step for it? Do I need to look at things that occur over long time periods and then sort of make decisions based around that? Okay, back to my slide. Okay, let me just catch up on some questions here. Which digital control can be fast to operate with this fast switching speed? I would say there's lots of things you can do. So just because we have a very fast switching speed doesn't mean our control loop needs to work at that rate. So with digital control, with some of the new TI processors, you can scale up the PWM drive waveform. So you can have like a 250 kilohertz PWM, but your base interrupt routine could be 25 kilohertz. So you can have a 10 times multiplier on that. So your control loops can work at a more reasonable rate while your switching speed is cranked up. Next question, please clarify if this resolution issue is same with 60 hertz AC systems. So 60 hertz, I think I answered that through what I was talking about. Can we change the x-axis in degree from time? Yeah, so there's questions about the waveform viewer. If you want to change what's going on down here, if you go to axis, you can change the x-axis variable that quite easily. And then did you add a probe? I think I answered that. And another thing you can do is when we're simulating, and I'll show you how you can do runtime variables and do polar plots or something while the simulation's running. So there's some other things to talk about there. Okay, coming back. Okay, again, so some more comments about what I was just talking about on this slide. So essentially, when it comes to these are more about how to generate a gating waveform in PSIM. So you can use a square wave source. It's pretty basic. I would recommend a modulation with a carrier. This allows for proper transition to close the loop and doing an AC sweep. And then simulating with dead time is typically unnecessary because it drives that small simulation time step. So only add in dead time if you really need to know the impact of dead time. If you're just putting it in because you feel like you should put it in, then that's not the reason to put in dead time. Okay, so let's look at some of those gating methods. Do I have that sim open? Okay, let's look at some gating methods. I've got a demo. Gating signals, here we go. Okay, so here are, again, so you're going to get all these simulations. Here's some of the variants of generating a gating waveform. So these are going to be for ideal switches, all of these guys. So if we look up at the top, here's our basic gating waveform where we've just got a square wave source, and then we would connect that to a MOSFET, and we'd be off to the races essentially, right? That's that. Or, you know, the next one would be something like this. So now instead of having this gating waveform, we're using a modulation signal and a carrier to generate our gating. So this, again, is the preferred method. Something along this line is going to be the preferred method. And then there's, you know, these elements are available here in control. So I'm using the comparator and the comparator with dead time. So this one has dead time built in, so we're able to add dead time now. Otherwise, it's kind of functionally identical to that. So, and then now you've got the complementary pair right there. And then further along this path, if you just want to put one block down and have it a little bit more obvious, so this one we're defining the carrier properties. This one is essentially, grab my little pen again, this one is essentially all of these built into one, right? So we can define our carrier envelope, our duty cycle of the carrier, and then phase delay or dead time if we want it. So that one is a good one to use. And then again, we've got the main signal and the complement of that. Okay, driving into some more interesting waveforms down here. So a lot of people ask about variable frequency, you know, for LLC simulation. So there is in the library, there is a switch control element that provides a variable frequency with a whatever duty cycle you want. So that's this main block, but under the hood is this. So what we're driving here is we are making we've got a variable frequency drive out here, and then we are comparing that. We're using this integrator to make a little 0 to 1 ramp that's going to ramp at whatever period the frequency is that we want. And then we're comparing with 0.5, which is going to give us our 50% duty cycle that's going to change with frequency. So this is nice. Now, again, cycling back to the time step question, what time step should I use? Well, if you're doing a resonant converter, remember PSIM is going to interpolate. So we don't need to really be, you're going to need maybe 50 to 100 points per cycle would be a good thing to have for an LLC. especially if you have a wide range of frequency operations, pick your fastest operating point, and then 50 to 100 points is going to be pretty good, because remember, we're interpolating, and so as long as your system isn't too complicated, wheels will fall off the bus if you try and have a really coarse time step, and then there's a whole bunch of other things happening in the system. So you've got lots of other things that are working. If too many things are happening inside of the coarse time step point, that adjustment can, you're starting to drive into issues where that adjustment isn't going to work too well. So definitely having a good time step is start coarse and work smaller as you add in more complexity. Okay, back over here. So let's run these now. Okay, so let's look at the variable frequency, and we'll look at this here. So we can see we've got a really tight little duty cycle right here. We're tight frequency, so we can measure that. So we're running over here. That's 1 kilohertz, 1.2 kilohertz. And then in the middle here, we've got, let's pick up the edges. We've got 720 hertz, and still with that 50% duty cycle. Okay, and so obviously this block is kind of what's going on under here, but it's not quite, which is why we've got that bit of delay there. The next question people ask me quite a bit about is phase shift or digital variance. So let's go to digital first. So digital means you need to put this delay block here, and this is the same thing as that. So this sampling frequency is going to be the one here. Again, that's enforcing our shift between but to the update of the carrier or the duty cycle at the beginning of the next period. Phase shifting, again, there's a block that's in here that gives you phase shift, so you can set the duty cycle. Duty cycle of the top of each leg. So this would be for full shift, phase shift full bridge topology. So you'd have 0.5 on both legs. And then we're driving into it a per unit shift value between 0 and 1. In this case, I've got a source here. We're going to be doing from 5 degrees to 85 degrees phase shift. And then this is how that would get implemented under the hood. So now I'm using that same method as before, where I've got an integrator that's giving us a ramp at that goes from 0 to 1 at the period we want, and I'm comparing with 0.5. Then my shift here is accomplished with adding in that shift into this in per unit, and then, or in this case, subtracting it because we want it to delay. And then we've got a range limiter here to make sure. The range limiter ensures that we stay within 0 and 1 when we add to the other side if we overflow. And then we just compare with 0.5 again. So we can run this, and we're looking at phase A and phase C. And we can look at with the elements as well. And if we zoom in at a point, we can see the shifting of those carriers on top of each other. Okay, so these are fun circuits to play with. Okay, next up. Okay, integrators integrate. So something that people kind of forget is that an integrator is always going to integrate. Unless you set the input to an integrator to 0, it is always going to start to accumulate. So that's one thing to always kind of keep in mind. So the best demo of that is this battery charger that I have here. So this simulation is set up to do this battery charger. So inside of here, I've got a sub-circuit, and that sub-circuit is a buck, and we're driving off a DC source, so 900 volts, and we're bucking to like 400 and something volts. And we're going to shift between constant current charge and constant voltage charge. And we're doing that with an inner current loop control, and then we've got an outer voltage loop that switches in. So let's run this. We can look at this as it runs, look at statement of charge. And we can see this is the flag to go to constant voltage charging off a constant current. Okay, now we switch to constant voltage now, and it finishes off the last little bit. Give it a moment here. Let me see some questions while I'm going. If you use the comparator dead time model but zero out the dead time, is that slow? No. The comparator model with dead time, if you put it to zero, it's functionally identical to the other kind. Okay, so I'm just going to stop this now. We don't really need to go too much further here. So let's pull up the current reference. Okay, so here's the reference current. And let's pull up the, this is the inductor current. So we can see we're clipping along quite nicely here, and then the constant voltage state kicks in and we ramp down nicely. Let's look at what's happening here in order to achieve this. Okay, first things first. This switch signal is our 0 to 1. So what I'm doing is when I'm not using the outer voltage loop, I'm feeding it at 0. Okay, that is critically important because otherwise this voltage controller, it's not doing anything if we're running on constant current. So this mux, I've got 0 feeding in, and then I'm driving this to 0 so that its output is going to be 0 and it's not doing anything. So when we switch to it, it's not going to wound up to some large value. So if we had just left this with an error signal, like the error signal from out here, this would eventually just wind up. And what that means is that it's just going to keep integrating. Like a PI controller has an integrator in it and is just going to keep accumulating that error because it's not doing anything. So this is key to remember, is your integrators are going to integrate. And the other thing you need to do is make sure that they're limited properly, because if you can get into instances where you get out of range. So the next thing we're going to deal with up here, so then the other thing I'm doing is this integrator, it doesn't necessarily care what its output is. So what I've done as well is I've preloaded the integrator value with my steady state current reference. So we can see that I've mixed in my reference here, and then all this integrator is going to do is when we switch to constant voltage drive, is it's going to take away from that reference, right? It doesn't care. Like I'm not setting my current reference IREF is the combination of my steady state constant current value and the output of my voltage controller, and we can see that's being dictated by trying to stay at 403 volts. So if I take this away, we'll see what happens if we don't do that. So now I'm just going to have this one going, and let me just get rid of my bounds here. And we'll see what happens when we don't have a nicely defined limit. So there's the voltage on our battery. There's this. There's the current into this thing. Here, let's go statement of charge. Okay, we switched over, and look at that. We've cranked up to 460 volts. And so let's stop. So this is another common problem I see. So our reference current went up to 300 amps before, when the voltage swapped in here. So that's no good. So that's what the issue is here with having an integrator that is not being controlled when you're not using it. So that's a key point to remember when simulating. And what's my next slide? Okay, so let's talk about troubleshooting for the last little minute here. So the first thing I always look at when somebody sends me a simulation that's not working is I check the modulation waveform. The modulation waveform is this signal right here. I make sure that the modulation waveform, so if we're looking at this, if we pull up VMA, the modulation waveform needs to stay within the carrier envelope. So in this case, we're between 0 and 1. The carrier envelope here has been defined as between 0 and 1, so that's okay. Typically what happens is these carrier envelopes can be, it can be too, you need to make sure you're inside of that and that things are and that's the first thing to look for. Other things that I look for is I check grounds. So if we have a circuit, this ground symbol, if I add another ground in here somewhere, what I've done is I've essentially shorted these 2 points out electrically. So we need to always remember, oh, I shouldn't have added that right there. And then also traversing across traces, we can easily short things out because PSIM will connect to any node, any point there. So if we wanted to connect across, we can go like that, and we see we don't get a dot there, so it's not connected. So now I've added that ground point there. I've shorted those 2 guys out electrically now. Other things to look for here. You should, if you're trying to run closed loop and it's not working, the first thing I look for is I go back to open loop to ensure that it's working or something similar as possible in the open loop. So are the LNC values big enough? Or maybe they're too big, especially in like an inverter type of simulation. You could have too large of an output capacitor and you're not able to shape that voltage properly. Other things to look for is if the converter goes into DCM for some reason. So because this changes the gain relationship. And then also the controllers are at limits. Okay, so let me just kind of look at some questions here. If you use, yeah, I answered that. Okay, when my simulation gets too complex, I always encounter memory issues. Is there a guide to how to handle that? Yes. So if your simulations get very large, there's a couple things I would recommend. So let's look at, right, okay. So let's look at that. I just need to close some things down here. Okay, let's run one of these ones. Okay. So I'm going to use the load flag. So I'm going to run the simulation. Oh, sorry. I'm going to use this save flag first. Save flag. What that's going to do is that's going to save the state of the simulation at 10 milliseconds. Okay? Then what I can do is I can use the load flag. And let's say we run for another 10 milliseconds and or another 5 milliseconds. So we're going to go to 15 milliseconds now, and I want to drop the time step down. So we're going to run at a 50 nanosecond time step for 5 milliseconds. What that load flag is going to do is it's going to start our simulation at 10 milliseconds. And you see that? So we've got the last 5 milliseconds only, and if we zoom in on this, we pull up the markers for the data points. If we zoom in, now we've got that really fine time point. So we were able to run that last 5 milliseconds at a different time point, and conveniently, we can also change any of these values. So we could run again with a 200 microhenry inductor there. It doesn't, as long as we don't change the matrix, we can change any of the attributes at this point. And this is really handy when we get into scripting. So you can write a script that will run a simulation to steady state, and then you could change the DC bus value, the resistor value, like any of the attributes, as long as you're not changing the matrix. By changing the matrix, I mean we're not adding in new components. Okay? So the load and save flag is a really handy way to split your simulation apart into smaller pieces and maybe look at certain pieces with smaller time steps, and all of that can be done with scripting as well. So you don't have to do that manually. So you can set up and automate all of these simulations. Let's talk quickly about AC sweeps. Okay, gating waveforms. And I realize I'm running low on time, so we'll go a little bit longer. This is the first time I've run this sort of webinar where I talk about these sorts of issues, and I realize that I've got probably enough to fill an hour and a half. So I'll run a little bit longer here as we go through, but let's kind of get to another questions here. There is, can you give a PSIM reference? Okay, well, I think we'll send you something after the fact. If I am working for integrated circuit with any fab, how to make my FET switches match them with fab technology? Okay, so that is an interesting question. And that kind of deals more with our level 2 devices and how some of the PWM ICs are designed. And that's a little bit too detailed for this webinar. But so we have a library of PWM control ICs. These are all modeled based off the datasheet and functional diagrams, and they all kind of work as the devices do. So there is, so the way these functional ICs work underneath the hood is they're basically a collection of flip-flops, delay elements, and current sources, and all that kind of thing. And we've worked to define these independently of the manufacturer. So we can send you some examples of how these are built if you want to get into that kind of thing. There's a question there about, is PSIM similar to MATLAB Simulink? Yes and no. So PSIM is by most accounts more robust and functionally and stable and faster than Simulink. Obviously, those are comparative to your computer and the type of simulation you're working, but in general, those are the cases. Like with Simulink, you don't have these various switch models. You can only run with ideal. You don't have the option to go to a thermal model. You don't have the option to go to a level 2 model. We'll talk about those in a moment here. I just want to talk about gating for a second. So we look at this here. So when it comes to a frequency sweep in PSIM, PSIM runs time domain simulations. One of the things I see with people when they do frequency sweeps in PSIM is they will run it like it's a frequency analysis, like LT-Spice, where you can run from 0.1 hertz up to 10 megahertz, and there's going to be no computational issues with that. PSIM is running discrete time domain simulations at each frequency of interest and extracting frequency content. And we're including the switching operation. So we're agnostic to the power stage. This power stage could be a peak thermal control or a phase shift or a variable frequency drive or an LLC or a motor drive or a three-phase inverter or a whatever. It could be a multi-loop system with multiple controllers working inside of it or whatever it is. We don't care. All we care about is that we can introduce a perturbation, and that at some point we can put our AC probe and watch the impact of introducing perturbation and what it does to that particular variable. Okay, so as such, we are doing time domain simulation. So let's look at what that means. So over here, I have a somewhat complex circuit set up, but what this is doing is we're going to ramp from 0 to 500 kilohertz. So we're ramping a frequency here, and then I'm generating a sawtooth that's going to be a per unit 0 to 1, which we're doing the sine of. So we're getting a sinusoidal modulation waveform offset, and then we're going to look at over here. So when someone sends me a simulation and they're running a frequency sweep up to 10 megahertz with PSIM and their switching speed is 50 kilohertz, that doesn't make any sense. You can't do that, and it doesn't work in real life either. So when we run this, we've got, so mod demo is our switching out here, and that is a mess right now, but we'll look at our carrier versus our, these guys, and then we've got our drive frequency. So this thing is switching at 250 kilohertz, or the carrier envelope is 250 kilohertz. So let's look at some results here, kind of keeping those two things in mind. So let's zoom in right at the very beginning here. So this is when we've got, so our modulation, the blue waveform here, we're slicing it nicely, and we can see the output PWM is nicely defined between the narrow pulses and the larger pulses here, and this is at 30 kilohertz. So our ratio between modulation frequency and drive and carrier frequency is quite good. As we creep forwards towards switching, over 2. So we got to remember Shannon's or Nyquist criteria. So here we are at 115 kilohertz about, and we can see we're still resolving it. Obviously, the ratio between modulation and carrier is getting quite tight now, but there's still some data there. We're able to resolve that, no problem. But as we go faster now, so let's look at switching. So if we go right around switching speed, so right around 250 kilohertz, we can see there's multiple, this is starting to shift. So we're getting a shifting, and look at the waveform here. So we've got an open duty cycle or a low duty cycle and then a small duty cycle. When really we should be getting, we're not getting that. So we folded back and we're getting what looks to be, if we measure that, if we kind of go to the big pulses to the middle pulses and say that's half a cycle, that is a 60 kilohertz fundamental. So we folded back to 60 kilohertz at this point. So, and if we go even faster, if we zoom in, say right here. So again, we can see we've got, if we go, we should be seeing, when we have that nice resolution of the duty cycle at the better ratios, we were seeing the duty cycle, the frequency in the PWM properly. So this is supposed to be 315 kilohertz, but we're seeing between the narrow pulses and the wide pulses now, like 200 kilohertz or 100 kilohertz. Like it just doesn't make any sense. So when you're running a frequency sweep, you need to understand what the engine is doing, and that is injecting points or target frequencies. They're being compared with the carrier, so trying to go to too high a frequency just doesn't work. That's where you start seeing the noise at the high frequency range. Other things that people do is they start adding in a huge number of frequency points. So we have several different methods of doing an AC sweep. The multi-sign method, you need to know steady state time, and then it injects frequencies. Again, if you put in, so the frequencies are injected in one blast. So in order to resolve subtle differences in frequency, that drives the Nyquist criteria again. So if you're asking for like 500 points, those all need to be observable and extractable, and that just drives a very, very small time step. So more than 10 to 20 points per decade is way too much data. If there's a resonant frequency in there that you want to look at, there's other options. Our main AC sweep element here is very easy to use. We have four types of AC sweep. I'm just showing 2 here. This one is the original one, and it's very robust. It does a steady state detection, so all you need to do is to find the perturbation amplitude, which typically is 10%, 5 to 10% of your reference point. So we're arriving at 0.275 here, so our start and end amplitude is going to be 10% of that. So when we run this, hang on. That's odd. Oh, I don't have, it's not enabled. There we go. So when we run this, we're going to be injecting 85 kilohertz, and this one is going to inject them sequentially. So we need to be cognizant that if we try and put a very low frequency in here, it's going to cause a very long simulation time because we need to run that frequency to steady state. So if we're switching at 250 kilohertz and we want to look at like a 1 hertz sweep, that you need to recognize that how many cycles the perturbation frequency do we need to have to hit steady state. If it's 10 cycles, 1 hertz, that's 10 seconds. And if you recall, like we were taking 2 or 3 seconds to run 10 milliseconds. So you can extrapolate out how long that's going to take if you try and drive really, really low frequencies in there. Other questions? How are we doing for time here? Okay. Questions. So here we can see that sweep result. So we went from 100 hertz. And if we were really interested in a lower frequency, we could add in one here. Or if we wanted to resolve this transition region, we could add in a few extra points here as well. Okay. Yeah, the next thing I was going to talk about was is the battery model configurable? Thank you. No, it's not. I've just set it up to run in that specific thing. You'd need to change it. You'll have access to it. It'll be included in the files we send, so you can play with it if you want to. But the current loop and the voltage loop are set up for that particular controller. Okay, well, hey, good question. Can PSIM simulate the effects of EMI harmonics in the encoder cable and motor drive application? Yes and no. So encoder cables are logic level. So you would need to add in some noise to them, but you can do that. Is there any magnetics model designs available? So there's a question about magnetics. So yes, so PSIM has lots of different non-linear inductors or magnetics possibility. So we've got, here's a linear inductor. Here is an inductor with a saturation curve that's piecewise, so in current versus lambda. And then we also have this one, which gives some hysteresis, and this one is a bit is different from this one, and also has saturation. And then if you really want to get into things, you're looking at building up a magnetics model with a saturated core. And now we've locked, and we can do an air gap in here too. So here now we have a realistic magnetic or inductor with an air gap. And if we were going to do with an air core, we would do something like this. So here's a E-core with air gap in each leg. We could wrap that around, pull that up. So here we've got our magnetic structure. So we've got an E-core, and we could add in our winding here with a proximity. So this is leakage path, sorry. So we can do stuff like that. So you can build up your custom magnetics like this. All the files and video tutorials that will be sent to the webinar participants who ask specific questions can be public available in some form with this webinar video after it finishes. We can try to include other ones. I'm interested in power electronics and machine learning. Can PSIM import TensorFlow models? I don't know what a TensorFlow model is. We can do lookup tables and C code. So you can have a C code guy here. The C code simulation can run a whole bunch of different things. You can define anything arbitrary in here. We can load a DLL file. So you can have a DLL block. This loads in a precompiled .dll. We link to other third-party tools this way. You can also have, if your data is a lookup table, we can load in lookup tables. So let's kind of quickly talk about our level 2 models here. So our level 2 models, let me just run the simulation. Our level 2 models provide us with a realistic device transition between on and off. And I've done webinars on our level 2 model specifically, so I'm just going to kind of touch on it quickly here. And so we've got the level 2 MOSFET here. We have level 2 IGBT as well. And then we have a diode with reverse recovery. And we've got our parasitic inductances here. So someone asked about adding in parasitics. Well, just drop them in wherever you want. You need them. Just put in a small little resistor, an inductor with some series resistance maybe, or leave it off. It doesn't matter. And then so here's some results. So this is a fairly small time step. Again, because now we're driving and looking at the actual device transition, we care all of a sudden about what that time step is. And it should be quite small in order to resolve these small little wriggles here. So this is the current through this MOSFET. We can look at the voltage across this FET as well. Let's zoom out a little bit and just look at, and we can see when we're at device operation, what's happening. There's a question, sorry, is where the phase shift function block can be found in PSIM. Okay, just if you're ever looking for an element, just go to library browser and type find and type phase. And then there's all the phase shift elements that show up there. If you're trying to do code generation with phase shift, that is a more complex answer. It requires, you should look at the code generation examples for a phase shift full bridge, and you can go help, search help, and if you type phase up here, you're going to get a whole set of examples and videos and links to all sorts of things that deal with phase shift. Okay, so back to this simulation. So here we've got this, and so now we can look at the switching loss. So we can, if we integrate the voltage across the FET times the current through it, we can see our pulses here. So we've got the turn on. Let's actually just look at this. So we see the sloping line. Come back over here. So we can see the turn on loss and the turn off loss, and we can see the conduction loss as well. And then we're able to look at, so if we look at P in total versus P out total, so I've got two measurements over here. So we're able to look at the differences there and also look at the efficiency of the system quite easily. So we're right out here, right around 0.94, 94% efficient between input power and output power. We would need to add in losses in the gate drive too if we really wanted to. So that's something with these level 2 devices we can look at. And this will be in a simulation that you can have a look at. Yeah, so I think without diving into a whole host of other simulations, this is kind of everything that I wanted to kind of cover. I think now I realize that there's a lot of content that I can fill here, and maybe we'll do another one of these in a couple months to show more common simulation errors and troubleshooting techniques and all that kind of stuff. We can have a quick look at our thermal simulation with this LLC. So this has resonant zero voltage switching, and we can look at our simulation here and look at the switching losses. So one thing that I know doesn't work so well in other tools is when you try and look at switching losses with zero voltage switching. So that's what we're looking at here. So let's look at voltage across VDS, and then I got my current probe somewhere, IDS. Let's add those two. Zoom in here and look at a cycle or two. And let's look at the gating. VG high. So we're turning the device on right here. So inside of this period here is when we're turning the device on, and we can see that the switching losses are actually zero. When we turn the device on, we're only showing the conduction losses essentially on the switch. Obviously, so this is switching without dead time. So if we added in dead time, there might be a couple other things to look at. But so we're bringing the correct or a good simulation of this particular converter when it switches on or off. So here we're turning off. So we've turned off right here. And again, we're not seeing any switching losses because, I mean, the voltage across it is off when it is switching. So our thermal model is capable of simulating the results of zero voltage switching and zero current switching on the losses. So there's other webinars that talk about thermals and tutorial videos and all that kind of thing. Okay. Is the worst case analysis and smoke analysis available? Not yet. You'd have to build it out of your script. Other things to talk about. I see Ray Ridley is in the webinar, and I should plug our link with Ray Ridley quickly. So one of the things to look at with Ray Ridley is that you can design, when it comes to designing your power stage and closing the loops, we link to tools like RidleyWorks and there's another tool called Smart Control for other things that you can, so you can design your power stages and then import. So I'll pull up a simulation that was an export from RidleyWorks, and we'll bring that across. So here's a 2-switch forward converter that came from RidleyWorks. And so this is the kind of thing you can export, and so it's closed loop. And so I strongly encourage you to look at Ray Ridley's Facebook group and the RidleyWorks design tool to look at how you can simulate things with, and so design your power stages and export them into PSIM and then run them. So yeah, so this one, and we could do here, and this one will run the loop gain sweep. So if you're interested in a mix design a little bit, you don't want to get into using our particular devices, Ray's tool does provide a thing as well. From 10, we're sweeping from 10 hertz here on this particular example. So this is going to be a relatively long simulation. Should be over a minute. It'll start speeding up here as we get to the higher frequencies. Oh, and it looks like Ray's chimed in. Loss model. It's run it with the core loss model on here. Let me just stop it, and I'll make it run from a slower system. I'm not sure why that was taking quite so long. It's what I get for running things that I wasn't necessarily planning on running. Oh gosh. Does PSIM take into account the proximity and skin effects in high frequency? Not natively, but if you use the export from RidleyWorks, that provides you with a ladder circuit, an RL or an RC ladder circuit that brings that information in. Further, you can link to, we link to an FEA tool called JMAG. So you can have your nonlinear magnetics defined in an FEA tool, finite element analysis tool, and that will allow you to analyze or look at those sorts of things as well. So definitely, PSIM provides you a sandbox. It's up to the end user at the end of the day to figure out how it all works. Or if we don't do it natively, you can ask us, we can give you some advice. But yeah, there's definitely, the bits are there. And it depends on how you want to do it. I think, is there a block to interface with the solver in for C code generation? Yes. Yeah, so there's questions. So we're getting a few questions about C code now. Yeah, so if you have a question about code generation, there is, as I say, there's a whole host of example circuits. If you want to look at a censored machine motor drive, just come into the examples folder, the SimCoder folder, and any of these censored examples. So let's pull up this PMSM. If we look at this, this is going to show you how the encoder inputs are brought in. Okay. Okay, my voice is starting to hurt, so I think thank you so much everyone for coming. We will talk again soon, I hope. Keep out for other webinars on other subjects, other interesting subjects. We'll do more webinars. We're trying to run a sort of a bi-weekly schedule here. Sarah, any other comments here before we all kind of sign off?
I just want to recommend everybody to follow us on LinkedIn, Facebook, Twitter, Instagram. We will always post recordings as well as live webinars, new videos, new tutorials, other useful content and news about PSIM and DSIM there. So it's worth it. And We promise we will try not to scam you or spam you with emails or anything. We just really want to give you good information about power electronics and motor drives and microgrids.
I think that's about it. Hey, Sarah,
Yes.
should we?
Yeah. No, great job. Thank you for presenting and sharing your time and insights with all of us. And we'll see you probably in a couple of weeks for our next webinar, which we will soon announce. So
Okay.
don't forget to follow us.
Okay. Thank you, everyone. Bye now.
Bye.